see what is the error, and then you get a overall error assessment of the clusters. Right? So that's what it does. Make sense?
Yeah, yes, sir.
Any other questions, folks? Where? Value counts. It just gives you the counts of how many different types we have. Yeah, all good. So then, if you can, folks, go to that link for the MBA Market Basket Analysis and download these files. Uh, First, download this file, which is called as I think it's here in the Quora link. The file name is example. So can you see whether you can download this file? Permission? You don't have the permission? Let me just send over here. Let's see. Am I in the wrong or the right link? Is this the right link? No, not even there. Day 3, day 4. Yeah, this is the one. Day 4 is the one. Okay, let me see if I can add the file. Hmm. Ashutosh, can you see if you can grab and send it to everyone? It says I have shared a file, but let's see if we can find it. Example, called example. And while you are going through this file, let's read these metrics. I'll give you maybe 5 minutes to understand what is support, confidence, and lift. Again, link to the article that you're looking at, and let me know once you've taken a look. Support, confidence, and lift. 3 metrics we'll be discussing.
So it's giving like asking for confirm your current password, something like that.
Yeah, so Ashutosh is going to share that in the WhatsApp. I just uploaded the file on the Teams, so he'll pick it up from there. And once you have the file, you can open up and take a look. But important is to go through this Quora write-up as well and understand these 3 metrics: support, confidence, and lift.
It's in the name.
Go ahead. Sorry. Acha, you got it? Not yet. Okay. Ashutosh, you facing any challenges?
Sir, I Astos I uploaded in the I think in the Outlook, but still I'm getting a
No,
confirm your
he's working
password.
on it. He hasn't done it yet. He's working on it.
Okay.
But you can use this time to read the Quora, understand what those metrics are while the file is getting ready.
Yeah.
Yeah. No, no, I sent that file no, to you when over here in the meeting group. Yes, sir. Yeah. Right? Me, right. This is Excel file. Yes, sir.
Do you want me to share it? I have downloaded it. I'll share it in WhatsApp.
Yeah, why don't you do that, I mean?
Uh, I have shared it in the WhatsApp group.
Okay. Awesome. Thank you. Now everyone has the access or yet to come? Shall we? We've gone through it. So there are few metrics which are important for us. The first one is support. Who would like to talk about what support really measures?
I think support is like we calculating a item set, how many items are contained. Like if we have three shops,
Mm-hmm.
and if we have an item set of like 1, 2, 3, 2, 3, 4, 1, 5, 6, then if I take support for one, then it's like it's 2 for one, because in three uh, shops the item
Mm-hmm.
has been selected twice from three shops. Is like that.
These shops. Yeah, it's more like the transactions. Like, I mean, how many transactions have that item is what you're trying to measure. Mahesh, you were adding on something? Same thing, yeah. So basically, it measures the volume
Hmm.
of the product combination, right? That's what the support really measures. What is the volume of that, right? Because there are many combinations, millions or maybe more than millions combinations possible. So how do we really look at the high volume products and focus our time and effort on making recommendation on them is what the purpose of support is, right? It's a measure of frequency, or in terms of the probability, what is the probability that item will be bought? We'll talk about that when we go in the Excel. I will show you when we go in the Excel, yeah. Confidence.
Product A, the condition probability is product number of transactions of product A, which also includes the product B.
Yeah.
It is just a conditional probability.
Hmm. Right, conditional probability, but left-hand side means something has already happened. If the left-hand side has already happened, what is the probability right-hand side will happen? Yeah. Or in the Python package, you will see that this is called the antecedent, and this is consequent. Antecedent, consequent, right? Or left-hand side, right-hand side. So what is the probability this will happen, given that this has already happened? So what is the probability that, for example, India will win the game, given that they have batted first and made 400 runs in a one day, right? So that is basically going to be a different probability versus not knowing that, right? So that is the concept of the conditional probability. In terms of the probability lingo, it's given like this. So what is the probability right hand side will happen, given left hand side has already happened? This vertical bar is given, which is nothing but the probability of both of these events to be happening divided by the probability of left hand side. Or in terms of the support is nothing but like this count of this product divided by the total transaction. So count when both right hand side and left hand side are happening together, divided by the count when left hand side is happening. That's the confidence. Lift is slightly tricky. Who can explain lift?
Was thinking so I could not.
I understood formula, but I got it out because of the support product combination.
Uh-huh.
Because here also, this is also involved with two products, A and B. So it is like support of A and B. That means total number of transactions, including both products A and B, divided by total number of transactions, divided by support of A and the support of B. Formula I had. But there in support, there is a product combination you just mentioned. How that is different with Lift? Because Lift is also having two products.
Mm-hmm.
That's where I got it.
Right, right. Absolutely. So the lift is basically, in more common term, you can imagine the lift measures the interdependence of the product. If the product have zero interdependence, lift will be one. That there is no lift when you buy product A versus when you buy product B, right? So when there is no interdependence, the lift will be equal to one. When there is a positive interdependence, then the lift will be higher. So for example, if somebody buys a cell phone, then what is the probability that you will buy a cell phone cover as well? Higher, right? So there's a positive dependence. So lift will be higher generally for those cases. Why it will be higher? Because it says I am looking at when both of these events are happening, A union B. Support of A union B is but nothing but where both events are happening. Divided by support of A times divided by support of B, which is the independent probability. What is the probability it will be raining in Dubai and Bangalore simultaneously? probability it will be raining in Dubai times probability it will be raining in Bangalore, which will be a very, very small probability. So it's saying basically, if the events were completely independent from each other, this numerator will be nothing but equal to denominator, support of A times support of B. In case the events were completely independent, then lift will be 1 if they are independent. If they are dependent, then this will be bigger than this because of the conditional probability that we've actually discussed that. So A union B will be bigger than A times B, and hence lift will be positive. Like the example I gave you, that if you've already bought the cell phone, probability that you'll buy a cell phone cover or the glass shield will be higher. Completely opposite also possible, that the lift can be less than 1. For example, if you just bought the refrigerator from LG, what is the probability that you will buy exactly the same capacity refrigerator from Samsung? Very less, right? I mean, because you've already bought that, then it's a cannibalization. Either you buy this or you buy this, right? You're not gonna buy both of them unless you're setting up a factory or something like that, right? So that's what the lift of less than 1 really means, that the products are cannibalizing each other. If you buy this, then the probability you buy another product is less, right? So for example, if somebody buys sugar, what is the probability they will buy the artificial sweetener? Less, right? Because either you buy artificial sweetener or you buy sugar, right? If somebody buys an artificial sweetener, what is the probability that they will buy a sugar-free protein bar? Higher, right? If somebody buys pure sugar and then you say what is the probability they will buy the artificial protein sugar, I mean protein bar at the or sugar-free protein bar, less, because they just don't go together, right? I mean it's basically telling you something about the product, right? So that's what the lift really measures, and we'll explain you once we get to that Excel step one step at a time, right? So let's imagine that we have this baby data. What do we have in this baby data? There are 5 transactions and 5 products which can be bought in any of these transactions. In transaction 1, milk and bread was bought, and none of these items were bought. In transaction 2, what do you think was bought? Butter was bought. In transaction 3, beer and diaper. Transaction 4, milk, bread and butter. And transaction 5, only bread. So let's do one thing. Support is nothing but the total transaction where milk was bought divided by the total transaction. So how many transactions milk was bought? 2, right? So 2 cases where milk was bought divided by 5 total. So support for milk is nothing but 2 by 5, 40%. How about support for bread? Support for bread is three transactions out of 5, 60%. Support for butter and bread, meaning they both were bought together. How many transactions where butter and bread both were bought? 1 divided by 5, which is 20%. Right? How about the support for butter? Support for butter will be 2 by 5. Right? Support for milk, bread, and butter? Like all 3 were bought. 1. No, but I'm saying support will be 20%, no? 1 by 20%, right? And support for beer and diaper? Support for beer and diaper will be 1 divided by 5, 20%, right? So that's what we are looking at. That's the support. I hope this is very, very clear, right? Which is the frequency of the transaction which are happening, right? Confidence. So the way you read it is, what is the probability milk will be bought? So this is the left-hand side. What is the left-hand side? Bread and butter. What is the right-hand side? Milk. Here, what is the left-hand side? Diaper, and the right-hand side is beer. Left-hand side is milk, right-hand side is beer. Left-hand side is milk, right-hand side is butter. Left-hand side is bread, and then right-hand side is butter. So the way you're gonna read is, what is the probability milk will be bought given the bread and butter has been bought, right? Which is nothing but, if you remember the math, support of left-hand side and right-hand side, meaning when all 3 of them were bought. Support for left-hand side and right-hand side, all 3 of them were bought. Bread, butter, and milk. Bread, butter, and milk. 1. Transaction out of 5. So the numerator becomes 1 by 5 divided by support for left-hand side. which is bread and butter. So bread and butter, again one transaction. So 1 by 5. So 1 by 5 divided by 1 by 5 is 100%. So we are saying if you tell me that there's a customer who has already bought bread and butter and have already put that in their cart, let's say big basket cart or some other cart that you actually having, then I am 100% sure that this customer is going to buy milk as well. So make a recommendation for the milk. Did you forget, right? Or people who bought this also bought this, right? So the moment I see that you bought the bread and butter, I'm going to make the recommendation to buy the milk. That's what basically it boils down to. Yeah, please come.
Madhu is your student. It's got promoted.
All right, congratulations. Madhu, man, you are rocking it all fronts, huh?
He was one of the very calm and quietly completed the
Crystal calm and quiet. He's a silent killer.
He got promoted and he followed into solutioning, product solutioning.
Product solution.
In the and he's doing one of the pet projects for us.
Capstone project. Who is the first one to submit the report?
Production, I
Yeah. Yeah, definitely. Congratulations. Congrats. No problem.
Thank you, Aki.
Looking forward to dinner party. After capstone. All right. So is this clear, people? Line 21. What is the probability beer will be bought given that diaper has already been bought? Which is the support of right hand side, left hand side, which is support of beer and diaper. Support of beer and diaper. 1 by 5. Divided by the support of diaper. 1 by 5. So 100% probability. Now this one, what is the probability beer will be bought given the milk has been bought? So this will be support of milk and beer. Remember, this is the equation that I'm looking at, right? And 1 by 5 divided by 2 by 5. Okay, let's take a look. Yep, 0 by 5 actually. So there's no transaction where the milk and beer was bought together. No transaction.
Yeah.
So support for milk and beer. How many transactions are there where milk and beer was bought together? Milk is here in these two rows. There is no beer. Milk is here, there is no beer. So 0 transaction. So that means if somebody has bought milk, I'm 100% certain that they will not buy the beer. So do not make that recommendation. You go and buy the beer. Right. So that's what basically it means, the confidence, that how confident you are that they will buy the next product, given that they've already bought this, right? Who can tell me the answer for line 24?
50%.
There is 50%. So
50%?
yeah.
Yeah.
Okay, so let's take a look. This is 50%. Why? Because support for milk and butter together, milk
Yeah.
and butter together, milk and butter is this one, right? 1 by
Yeah.
5 divided by the support for milk, 2 by 5. Again, look at this equation. This is what we're looking at, right? Support for butter bread, support for butter given the bread has been bought.
That's also 50%.
Huh?
33%.
33%. Okay. So how many transactions where bread and butter has been bought together? Bread and butter has been bought in one transaction. That's 1 by 5. Divided by how many transactions where bread has been bought?
3.
3. So 3 by 5. So 1
Yeah.
by 3, which is 33%, right?
Yeah. Yeah.
That's the support and confidence.
So the way simply I'm reading that table is if you take the last one, for example, bread. So look at all the bread equals to 1, eliminate all of the rows. And when bread is equals to 1, so how many times butter is 1 or not? So in this case, only one time it has butter has been bought. So 1 divided by the 3. Okay.
Yeah. Right? So these are the simpler ones. Support, which is nothing but the frequency. Confidence, which is nothing but if left hand side has already happened. From those transactions, how many side transactions have the right hand side? Is basically what the more simpler version of this is, right? Yeah, your question.
That is union, right? Probability of
This is the intersection. Yeah, union is the other one. U. So that basically boils down to this, which is the support definition. Support of left hand side and right hand side, where they both have been brought together, which is the intersection. Union meaning either this or that. So union is like, what is the probability? It will be either sunny or cloudy today. Two outcomes are possible, 100% probability. What is the probability? It will be sunny and cloudy together, 0% probability, because either one will happen, right? So that's what basically it means, right? So support, confidence. Next one is the lift. And lift is nothing but this definition, which is support of A union B divided by support of A times support of B, which is nothing but support of A and B. So I'm going to do one of them. So what is the lift of butter? What is the lift for butter given the milk and bread has been bought, right? So what is this boils down to? Which is this formula right over here, support of A union B, which is where they both have been bought together. I mean, it's not A union B, actually it's the support of A and B, right? Where they both have been bought together, which is the right hand side and left hand side. So milk, butter, and bread has been bought together. Milk, butter, and bread has been bought together by one in one transaction. So that's 1/5 divided by support of A. Support of A is nothing but milk and bread. Milk and bread is how many transactions? 1, 2. So 2/5 times support of B, which is butter. Butter is 2, right? So the lift is coming out to be 1.25 for this, which means there is a positive relationship. They are complementary products, right? So if somebody buys the milk and bread, they provide a positive lift, right? Lift should be either neutral or positive. That's what basically it boils down to. Who can tell me the lift for the bread and butter?
It's 0.83.
0.83. Okay.
Yeah,
I don't know.
0.83.
Let's see. So support for bread and butter together, will be one transaction. So 1/5 divided by support for bread. Support for bread will be 3/5 times the support for butter 2/5, right? So that will be 1/5, 2/5, 1/6, whatever that number turns out to be. I'll just do that. 0.83. Right? Anyone needs a refresher on this before I give you the example that you will work in Python? This again, you don't have to do by hand in Python. I mean, it's all automated.
So what does really lift indicate? The significance of lift.
So lift of more than one means products are complementary. If something is bought, then it will enhance the probability of other item being bought. Lift of more than one. Lift of one means that this numerator will be equal to denominator, which is the events are completely independent. So if the events are completely independent, the probability of both of them happening together is nothing but probability of event A times probability of event B. So then the lift will be 1. If they are cannibalizing each other, that if one has happened, the other will not happen, less likely to happen, then this will turn out to be lower than the denominator and the lift will be less than 1. Lift will be less than 1, but not less than 0, because it's a numerator and denominator. Ultimately, probabilities cannot be 0. So numerator is a probability, denominator is a probability cannot be less than 0. So the lift cannot be less than 0, but the lift will be less than 1, equal to 1, or more than 1. Right?
So lift less than 1 indicates?
They are cannibalizing. Cannibalizing meaning if you buy this, then you don't buy the other one. Let's say if somebody is trying to, let's say when you signed up for the race program, if somebody came, let's say Great Learning came at the same time and say, by the way, buy my program also. Given that you've already bought the race program, your probability of signing up a similar program is lesser. So your lift will be less than 1 for that
Okay.
item combination. So if I were to make a rule that if somebody buys the race AI program, sell them the great learning program, right? So then the lift will tell you, no, that's not a great idea. Because if somebody buys a race program, then they are very less likely to buy the other one.
Okay.
That's what.
The word mutually exclusive can be applied to lift equals to 1.
If they are mutually exclusive, then this will be the case, which is like they are completely independent. When they are completely independent, if they were to both happen together, that is nothing but probability of event A times probability of the event B. So let's say if I flip the coin 2 times and it's a fair coin, what is the probability of getting ahead? 50%. Head and tail. Probability of getting ahead is 50%, right? What is the probability if I flip the coin 2 times? Both of the times I get ahead. What is the probability? If I flip a fair coin, what is the probability if I flip it twice? Both times I will win the head. 0.5 times 0.5, which is 0.25. So the probability is very small, right? But it happens, right? So I mean, for example, I think in one of the Indian captains in cricket kept on losing the toss, like 5 games in a row, they lost the toss, right? So what is the probability they will lose the toss in one game? 50%. What is the probability they will lose the toss in the second game? 50%. Third game, 50%. Fourth game, 50%. What is the probability all 5 times they will lose the toss? There's nothing but this number. Because they're all independent from each other, right? To the power 5. So it's this much small, which is only 3% probability that they will do that, but it happens. 97 probability that it should not happen, but 3% probability it will happen. Why I did the raise to the power 5? Because I'm multiplying 0.5, 0.5, 0.5, 0.5, 5 times, right? So that's the independence. Okay.
Sir, you said there is no interdependence which is equal.
Correct.
That means neither A nor B.
No, A does not affect B. They are independent. It's testing for the independence.
And cannibalizing, you said
Less than 1. Less than 1.
by A, I need that by B.
Correct. That's correct.
Positive interdependence. Higher.
Correct. That's correct. That's correct. Yeah. So if the lift is more than 1, then there's a positive interdependence. If lift is equal to 1, no interdependence. If the lift is less than 1, negative interdependence. Right. That's the interpretation. Confidence, lift, support, they should be all as high as possible for us to get good rules. Because what does the support mean? That it's a high volume combination. There could be 1 or 2 people who buy weird product combination. But we're not gonna go there and make the recommendation using that, right? We see what is it that majority of the people do when they buy this, what is it that they're buying. That's the support. Confidence says what is the likelihood that if this happens, then the other event is gonna happen, right? And lift says, are the product positively affecting each other, negatively affecting, or independent? That's what the lift is. Now what I'm gonna ask you to do is I will share this data with you, retail data. Can you check, Ashutosh, if this is there already in the previous batch AI03? Can you grab it from there? I think that will be easier rather than me trying to put it. You can access the LMS, right? In LMS for AI03, you will see this file, retaildata.csv. So while he's doing that, I'll just explain you what we're going to do. And you can get started with installing this package. This will be required. If you're doing in the Colab, then not needed. But if you're doing that in the Jupyter, you need to install ML extend, which is the extension of ML package. So you'll have to install ML extend. And I think the command that you can use is conda install ML extend. If you're doing in Jupyter, if you're doing in Colab, no need. It will be automatically installed for you. So you can try either one of them or run all of them, then see what really comes out from there, right? Just go and in the Google type conda install ML extend, and you will see what exactly you have to type it in. But the bottom line is once you've done the installation, it should be able to import these packages. So I'm going to give you some time to install this package and make sure the line number 1 is working for you while Ashutosh is trying to bring the file to you, right? So for me, the line number 1 is good to go. So that means all the packages are there. If you're doing in Google Colab, you don't need to install anything. If you're doing in the Jupyter Notebook, definitely need to install.
Sir, could you show us that command thing that you are showing?
Yeah, just type conda install
Oh.
ML extend
Okay.
and then look at the first link and then grab this and then try to run the command, the line that I have in the code. If it doesn't work, try to do this. If it doesn't work, try to do this and so on and so forth, right? I'll just put it on the chat window. Let's see. Okay, so for Mohit, pip install is working, which is fine. You can also try pip install ML extend.
Please show us the other screen, sir.
Hmm?
How we test if it's installed. Yeah. Okay.
It's same thing in my blog as well. You can refer to the blog. Are you done? This code is working for you. No? Pip install or Conda? Yeah, Conda or Pip. Pip install worked. How about you? Google Collaboration. Then you don't have to worry. How about folks online? Anyone struggling with this?
No,
Detail Ashutosh is bringing in. Huh. Corrected? Yeah. So then you can follow along the blog. Come to the stage where you're reading this file. Doing all of this that I'm showing you. Coming basically all the way till the stage where you have the rules, right? And if you're looking at the blog, what it means is following that you are following this example, the first example, and ending over here. So don't go to the example two. So I'll give you maybe around 50 to 20 minutes to make sure that you copy paste from the blog, type your code, and go till the end of first example. Then we'll come to the interpretation of that. Ashutosh will send you the Let's touch base. Yeah, not okay. Anyone is able to open or no? Retail file. Retail file is not opening. No, the Excel file is not opening. Can you share your version, Mallikarjun? It's working. It should be read Excel. Acha. Okay. So just do an info on that file and see whether everything is good. Yeah, all good. Can you ping me, Ashutosh? I'll send you this file from my end. Like just ping me on the Microsoft Teams. Huh? I don't have Outlook on this machine. Just ping me on the Teams and then I'll send you this file. Because I don't know, I mean, how to get to this right group over here. Because when I go to the file, right class doesn't show.
So do you want me to share the data set, is it? Retail data set?
Yeah, why don't you do that?
Yeah. It's working for me and everything. I'll share it in the WhatsApp group.
Oh, perfect. Thank you.
Yeah.
Yeah, might be. Might be.
It's working for me also.
Yeah.
The one which I'm sharing, it's in CSV file format. So.
Got it.
Done, sir.
Thank you, Amin.
So the code part is also done.
Code is done.
Yeah.
I think some of the folks are working on it. Great.
So are we gonna do the online retail as well, or
No,
just?
no, just the example one. importing all the packages, reading the file, doing the head of the file, all the basic diagnostics, right? So it should look like this. Can you confirm that you have 2000 non-null data, everyone? Yeah. Okay. And then this is where we're going to drop the transaction ID. So remember, we have a transaction ID that is not required. We will drop it. And then we are describing this. Basically, include all means that we're describing it. So this code may look slightly different to what you have, but don't worry about it, right? So, but the more or less, I mean, you will see that I'm just following the same. What does this line do?
It's
Remember?
convert all the categorical value variable into numerical.
Yeah, right. Remember, there were two ways of doing that earlier. I was telling you that you have the imputer or you have for loop, you have other ways like the mapping. This is a must-have for the MBA algorithm, for the a priori algorithm, that each of the product is created as a column. So it's not like that we are just using the get dummies because we want to, but each of the product will be created as a column. So for example, how do we read this? In first transaction, bread was bought and butter was bought. But there was no fruit, no juice, no nachos, no butter, and so on and so forth, right? And then you can keep on scrolling to your right to see what else was there, right? So basically, in first transaction, dairy, butter, and bread was bought. Dairy, butter, and bread. So you can see butter, bread, and dairy. Rest of the transactions or the product were not there in the transaction, so everything is flagged as a zero. This is the format you must have for building this algorithm. And they are 0, 1. We don't care whether 100 items were bought or 2 items were bought. We just say whether it was there or not, right? So that's what we are doing. Any questions so far? Okay. And this is where we are building the rules using this algorithm, right? So a priori come in from the ML extend. We are passing on this new data frame, which is 0, 1 dummy coded. Min support is 0.02. What do you think this may mean? Right. So that means only build those rules where the minimum support is 2%. So at least 2% of the transactions are there for that rule. Only show me those rules because we don't want to look at the rules which don't have a volume, right? And we are using column names and we are sorting by the support. So you can see this is how the data looks like, right? So for example, how you will read this is that 57% of the transactions have egg from the total. 35% of the transactions have bread. 34% of transactions have jam. 25% of transactions have egg and jam. 25 have bread and egg, right? And let's come down. Like this one, juice, egg, and jam, all three together, 20% of the transactions. Is this clear? What are these rules telling you? Just looking at the support that we want only those transactions which have a minimum volume that we require. Okay, let's continue. And then here we are building the rules. So basically association rules will be like, it will flip flop the left axis and the right axis together, right? To build those different rules. And that's where the definition of antecedents and consequent is coming in. So we are saying frequent items, the prior code that we have created. Metric is going to be lift, minimum threshold is going to be 1. So I'm saying only build those rules where lift is a minimum of 1. I don't want to see any rules where products are cannibalizing each other. Only give me those rules where lift is a minimum of 1, right? And it's going to build those rules for us, right? And then we are actually saying the shape and all of that, and we're going to sort by the lift. So you can see here, this is sorted by the lift. So smallest lift to the highest lift, and you can flip that as well, right? So these are the rules, right? How do we interpret these rules? Anyone would like to tell me what this line 31 means really? Any one plain English definition, if you can tell me for line 31 or any of these lines. Hmm. Okay. Yep. Okay. So it means antecedent means what is left hand side? Egg is left hand side. Consequent meaning right hand side.
RHS.
Right. RHS. So it's giving you a rule. If I know egg has been bought, I'm telling you what is going to happen with salsa. So it says there are 57% transaction where antecedent support is there, where egg has been bought either alone or with combination. There are 19% transaction where salsa has been bought either alone or with combination. And there are 11% transaction where both egg and salsa have been bought either together or with other products, either just with two of them or other products, right? There is a 20% confidence. So for example, if somebody bought egg, if 100 people were carrying egg in their basket, only 20 people will go and buy salsa. That's the confidence. Lift tells you that there's nothing to worry about in terms of the cannibalization. So if somebody buys the egg, it doesn't mean that they will not buy the salsa. They're not the same product. They're different product category altogether, right? But it's not necessarily a very solid rule because the confidence is fairly low, right? So here we can sharpen our focus a little bit by defining certain things. So for example, rather than looking at all of these, I can say from the rules overall that we have built, only show me those rules where lift is more than one or equal to one, so that there's no cannibalization. Confidence is 80%, that we are 80% confident in something is going to happen, and minimum support is more than 20%. So from those 89 rules it has built, now it is giving you those rules which make sense, right? So for example, let's look at this interpretation. Antecedent is butter. That means butter has been bought already. Consequent is bread. Then we are making a prediction about what should be the bread's game be, right? It says 24% transactions where butter alone or something else with butter has been bought. 35% transaction where bread or something along with the bread has been bought. 21% transaction where both of them were bought together. So fairly big chunk of transaction where both are sold together. And 87% confidence that this will happen. So if somebody has bought the butter, there is 87 probability that they will buy bread. So very, very good rule. And lift is 2.47, which is like, I mean, big positive interdependence. They're not independent, big positive interdependence, right? So that's what basically it means. Let's look at another rule. Probably maybe a more complex rule. I don't think we have. Yeah, this is the one. Like, I mean, here you're looking at two products. If somebody has bought juice and egg, juice and egg have been bought, 20% transaction where jam will be bought together as well. And the confidence is 96% that if somebody has bought the juice and egg, they are 96% likely to buy the jam as well. And lift is 2.83. This is all made up data. I actually created this data. So if you want to work on the real data, the other example that I have in my notebook, which is a slightly more bigger data. So you can play with this, right? This data right over here. So you can see it's 5.4 lakhs, right? Or 500K observations. So that's a fairly large data. I'm not going to ask you to do that in interest of time, but you got to hang off, you know, what exactly it means and how we build it. So I'll take a pause and open up for the Q&A. Last column, we haven't discussed that, so you can ignore that. I mean, there are in fact two other metrics, leverage and conviction, but we don't use them that often.
Antecedents and consequence
Hmm.
from data we have.
Hmm.
Let's say 87% is the
Hmm. Hmm.
If we reverse, that means it's a bread, antecedent and the rest is
Yeah,
same.
it will not happen the same way.
Same.
It will not happen the same way. That's what the probability is all about, right? So your starting universe is different. So it says, okay, all the transaction where bread is there, how many from there I can find the butter? Then starting universe for there is out of how many transaction I have butter, bread is there. So it may not be the same thing. most likely it won't be the same thing. That's why it does both. It does the crisscross of all the products. Like, I mean, if I do this and all of that, it's ultimately probability that you're starting with this denominator or that denominator. And then the numerator flips. And then you're trying to figure out what really happens. Right? Other questions, thoughts?
Is this computationally as intensive as
It
random
may
forest?
take some time. It may take some time, but the good thing is there is no algorithm that you're fitting. It's just computation, right? So it's not trying to do the like hyperparameter optimization, anything of that nature. It's just probability. So it's all it is doing is math underground, right? So it's not that much time consuming actually.
Okay.
Okay. On that note, shall we take a 15 minutes break for tea and then come back and then we'll cover the last topic, which is the PCA. Folks online, we'll take a 15-minute break, 3:36, which means what? 3:51. Yeah.
Yeah, sure, sir.
Okay. Come. We'll grab some tea, coffee. I think I generally release you in the very late time, so you don't get anything. So today you'll have the chance. All subjects together. Suddenly all subjects together 200. Spelling needs test. Okay, sir. After each module, we can have a practical. Shall we begin? Anyone who's missing? Folks online, are you back?
Yes,
No?
yes, sir.
Okay. So we will talk about the last topic for the day today, and probably for this module because we don't have a fifth class, which is what we call as a PCA, Principal Component Analysis, right? Throughout the day, we have learned three unsupervised model. What was the first one? Clustering.
He means clustering.
No, unsupervised, clustering.
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 And then the recommendation or the MBA. Next unsupervised learning algorithm is PCA. Does anyone know what does PCA stand for?
Principal component.
Yeah, principal component analysis, right? Now it can be used for many, many different things. So one is to remove the noise, right? Like, I mean, if you have too much data to deal with, you want to declutter some of this data and only focus on the signal. That's what the PCA is used for. To reduce dimension, this is what we will be focusing on. And what is dimension? Dimension is axis, basically, right? So that's what the PCA is going to be used for in our case. To fix multicollinearity. What is a multicollinearity?
Two independent variables.
Yeah, that's correct. So when x1 is related to x2,
Independent variables having correlation.
right, right, and x2, x3, x4, they're all interrelated. That is called the multicollinearity, and there are algorithms which don't like that multicollinearity, right? Like a linear regression, for example. So it helps us reduce that multicollinearity. And finally, to reduce the compute resources. If there's too much dimension, the amount of computing power that you require will be very, very high. So that's where it basically helps you to reduce that, right? And there are many other benefits. So I'm just talking about what exactly it means, right? So let's just focus on the use case of reducing dimension. And of course, the other things are the benefits. So reducing dimensions of the data, and the other things are the benefits of that, right? So what does the dimensions really mean? So for example, if I have x1, x2, x3 till let's say x25, that's probably too many variables, right? Because I have some interdependence in the variable and all of those things. So once I run this program through PCA, what happens is it will generate P1, P2, P3, P4 till let's say P25, which will be like reduction in the dimensions, right? But if the number of components is exactly similar to number of dimension, then how are we reducing it, right? So we don't select all of the components. Maybe we'll select, let's say, P1 to P4, right? And what happens when you do this, when you select P1 to P4, is basically your dimension. Let's say my original dimension was 25. Just imagine that my original data has 25. My new data has 5 components, and I'll talk about what those components are. So my new data has 5 components. So what is the number of dimension, or what is the reduction in the number of dimensions? Can anyone tell me by how much the dimensions have gone down? Right. So 20 by 25 is the reduction, right? So 4, 5, so 80% reduction in the number of dimensions, right? But if there is no free lunch. If you're cutting down the number of dimensions, there's going to be certain thing that you have to pay for it. And what is it that you pay for? Is the explainability of your data. So let's say your original data was having 100% explainability. Your remainder data, maybe the number of components that you selected, maybe will have, I don't know, let's say 70% of the original data's explainability. That's a great trade-off. The trade-off is that you're letting go of 30% of the data's explainability and only and reducing the number of dimensions by 80%. So that's a fair trade-off that I'm actually gaining a lot in the process, right? That's what basically it boils down to, right? Now the million-dollar question becomes, what is these components, right? P1 is nothing but a linear combination of all your independent variables. So if I had 25 independent variables, you can see that this is how the principal components are formed. My P1 is nothing but a linear combination of all the independent variables. Similarly, P2 is nothing but I'm going to use a beta 1 x2, beta 2 x2, beta 3 x3 till beta 25 x25. That's P2, right? What could be P3?
Gamma.
Gamma 1, and then you get the drill, right? This is how basically it's going to be. That's what the PCA really does, right? There's a lot of math which goes behind that, which is a singular value decomposition, matrix rotation, eigenvalue computation, covariance computation, all of those things. I'm not going to go in a lot of those mathematical because that's like a pure linear algebra matrix computation. But basically, what it means is it will compute covariance. Covariance is if I vary variable x1, how the variable x2 will change along with that, and then it tries to do some matrix rotation and all of that to come out with these linear combination of the things, right? So the gain that you get in the entire process is that it will help you reduce dimension. It will give you those P1, P2, P3. So for example, if I look at the correlation matrix, and I'll show you in the live demo, if you look at the, let's say, correlation of x1 to x2 was 70%, linear correlation in your correlation matrix, the correlation between P1 and P2 will be 0%. They will absolutely be not correlated at all. That's the benefit, that you get the components which are orthogonal, not related to each other, and completely independent, right? So that helps you basically reduce the dimension, fix multicollinearity, and because now you are cutting down your data, you will see that your model runs faster because it doesn't have to run through the data, right? So I'm just gonna create that example for you. We'll be working on this wine data. I think it has 178 rows and 13 columns. When I look into that data, when we do the PCA, rows will not change. Your independent data will remain the same. But what will come down is the number of columns, which is the dimensions, right? So you'll see that now we will have 5 components when we finish our PC exercise. So 178 rows remain the same, 13 columns become 5 components. So that's where the dimension reduction really comes in. And we will see this will also, it will do basically these things. So it will help you reduce the dimensions. It will help reduce, or I mean, eliminate, not reduce. Multicollinearity will be 0. And if you fit a random forest model, you'll see the model fitting takes less time. And it may also mean more accurate model, particularly cases like a linear regression, more accurate model. So all of these benefits are something that you can get when you do the PCA. So I'll take a pause over here, just a concept wise. Is it clear? Anyone? If you have thoughts, let me know. PCA can be
How
applied
would
whenever you think that there are some intercorrelation in your variables, or you may have thousands of columns.
Minimum column.
I'll say generally, if you suspect that there's very strong interdependence in your variables, you should try a PCA. If you think like you have hundreds and thousands of columns which will not fit in your model or will take longer to fit in your model, you should do a PCA, then go for it. PCA also is a distance-based metrics, right? So what should be the first step before you do the PCA? Scaling of the data, right? So if you don't do the scaling of data, your PCA will go completely out of toss. Because again, it's a distance-based metric, right, that we're looking at. So just make sure that you scale your data first and then do the PCA. Is that clear?
Actually, validation, dependent variables, either highly positively correlated or negatively correlated, we used to remove, we used to drop those.
We don't need to do that.
How different that and from this?
It basically
Automation of that.
Yes, yeah. It basically eliminates the need for you to manually remove anything. But your variables will go out. It won't be x1, x2, x3 anymore. It will be p1, p2, p3, p4. When I do the example, then you'll get clarity. But then you don't have to do any of those redundant variables removal by hand, right? So I have an article as well. You can read through it, but I'm just being sensitive about the time as well because I do want to talk about the exam maybe for the last 10, 15 minutes, right? So this is the article number 30 that you can take a look later on. 30, right? But I will do this. I will open up my example and ask you to follow along with me. I will go line by line so that you know what I'm doing. Right. And I'll copy paste maybe some of the codes as well so that you can do it faster. Okay, so this line of code everybody knows, right? I am looking at this data. I'll share this code so you don't have to type it manually, right? So this data is the wine data, right? And when you look at the wine data, you will see that heat map is suggesting that there's a lot of intercorrelation, right? So the darker the color, that means higher the correlation. So for example, you can see minus 0.4 correlation, sorry, plus 0.4 correlation, plus 0.49 correlation, all of those things. A lot of interdependence in the variables, right? What we're going to do is we will do some descriptive statistics on it and so on and so forth. Create our X and Y separate. PCA never runs on Y, only on the X, because it is trying to reduce the number of dimensions. Only on the X you do the PCA. Scale our data. In this case, we are doing a standard scaling, which is the the standard normal distribution or the Z distribution or the Z transformation, right? And then I don't need to do the model selection because I'm not building a model, so you can ignore that. But if you were to build a model, you will go through this flow, right? And then will not follow any of this. And then we will import our PCA, right? SQL decomposition, import PCA. We will fit on the scaled data, X scale data. And you will see that it will generate the number of components, and I'll explain what these values are once you are able to run with me. And then we will figure out what is the right number of components. We will build another PCA, and then we will do the some descriptives of the PCA, and then we will plot our components, right? And then we will do fit transform. Remember, I told you that once you create the instance, you will do the fit transform. And then as a result of that, your X data, which was having certain number of columns, will now be reduced to 5 components only, right? And I'll show you what those components are. Then we will do a heat map to show that none of these components are interrelated to each other. So it has 100% eliminated your linear correlation or any sort of correlation that you're looking at. So now it is completely kosher for your linear regression model because it has an assumption that the variables should not be interdependent and all of those things. So now you have fixed that problem and then you can go and plug it in, right? So that's what we're going to do briefly, right? Now, I can share this code with you, but then you'll get confused because I have done a lot of things in between. So what I'm going to do is quickly share the snippets with you that you should run, right? And then let me know if you're good to go from there, right? So this I'm not giving you, but you should create a file first, which says PCA. Don't copy the random forest and all of that. Just say PCA, right? And once you've created the PCA, then this is the file that you should import. So I'm just gonna share this code with you in the chat window. And let me know once you have these 2 lines of codes done, right? So interactive cell and then importing the file. And then you can go ahead and do the heat map as well. That is the same code, interactive cell.
Code interactive.
Same that you've done earlier on. In the previous code, every code we have this. No, we're not doing that. We're not doing that. That is down. Somebody's phone is vibrating. Then these two lines, folks, or yet, yeah, just copy paste the same code that I sent. Okay. All right. I'll give you maybe some time to figure what is wrong. Anyone online having any struggles? Yeah. No, no, it's okay. You can take a look. No problem. Anyone online who is having challenges?
No.
Okay. So you can finish up to the heat map. Now import Seaborn as SNS. One more thing. Figure size. Working fine, right? Fifteen by 15, the same code or different code? Same code. There you go. Right. That's good. Yeah, so it's too small actually. There you go. Right. So everybody is still here. Mallikarjun, you have the heat map, right? So you can see that there's a lot of variables which have the interdependence, right? So class label, let's forget about the class label. Let's look into the alcohol. Alcohol and this last variable, which is proline, alcohol and proline have 0.64 correlation, strong correlation.
Total phenols and flavonoids has got 0.86.
Flavonoids, where is flavonoids? Flavonoids is here.
Total phenol.
Yeah, you can see even the diluted wines, like this, whatever that number is, that is also very strong. This is very strong. And then total phenols and flavonoids is 0.86, as Mahesh is pointing out, right? So there is a multicollinearity in the data, right? So that proves it. So then what you can do is, you can do a quick descriptive of your data. Totally up to you what you want to run. So just do the shape, head, class label, size, whatever you want to do, right? So just totally up to you. I mean, I'll let you do some descriptive and give me a go ahead that you have done it.
Hello.
Yeah.
Sir, is there any link we need to follow, or just we need to look and type?
No, the same thing that we are doing on the screen. That's all. Same thing.
Okay.
Now we're looking at some descriptive. So you can do shape, info, things of that nature. like all the variables that you're looking at.
Sir, can you copy paste this line?
But it's totally up to you, you know, how much descriptive you want to do.
Just the last line I meant. Okay.
I put everything. Shall we? Yeah. All of this is just to do some descriptive statistics. So I will jump ahead now. This is important. So you should break your X and Y because it doesn't run. The principal component doesn't run on Y. So you should break your X and Y. Yeah. All good. So X and Y is separated. What we're going to do next is scaling. And you can do the min-max scaling or you can follow this. But this is doing the Z transformation, which is the -3 to +3 standard normal distribution. Shall we? Done. So X and Y is done. Scaling part is done. I'm gonna skip this one. Skip this one. None of this is needed. We'll directly jump onto the PCA part because that's where the new things are happening. There we go. Right. So from sklearn, decomposition, import PCA, and you have to fit on the scale data. Not yet, not yet. We're just fitting because we're trying. It would have been, fit transform directly, or this method works differently. Let me just take a look. Yeah, so scale X will automatically convert that. So this is a slightly different method. This is not the min-max scaler, right? So X scale automatically will scale that X. So I'm just passing on that as a function there, right? It's automatically going to handle that. And you can confirm in the values that you're getting, right? So you will see the mean will be close to 0 and standard deviation will be 1, standard normal transformation, right? And the max, depending on the outlier and all that, will be around 3. This is not min-max. This is a standard scaler. You know the standard scaler, right? Yeah. Mean is 0, standard deviation is 1 for that distribution. That's correct. It's a slightly different method, but yeah. And then what we're doing over here is the PCA, which is this on the scale data. Are we done for this? And then let's execute this line also. You have done it, right? This line also. And let's execute the next few lines, and then I'll explain you what we are doing. All of that. With the PCA5 also you have done. Huh? Acha, okay, got it. All right. So from yeah. Okay, no problem. And then you will do this, which is creating this data frame. After you do the 5 components, you create your data frame, and are we done, people? Then we'll go and plot this, basically this weightage that we're looking at. Or let me do this actually in interest of time, because we're approaching the 5 o'clock mark here. I'm just going to explain you. You can do the typing later on because we're almost on time and I would like to talk about the exam part as well. Ashutosh, I'm going to send you this. If you can be of help to share with everyone. Otherwise, this is going to take long, right? So all of you have the code. You don't have to worry about the typing part now. Just a quick walkthrough of this entire code. This is interactive shell that you're all aware of. Getting our data, understanding the correlation among the variables that, yeah, this is correlated. Then we did some descriptives, which is nothing unique. X and Y separation, as we've done earlier. This is where we are doing the scaling because it's a distance-based algorithm. Scaling is a must-have.
Why we cannot apply in standard scaler?
Sorry?
Can you apply standard scaler also there?
Yeah, you can do the min-max scalar, any other scalar.
Minimum scaler. Okay,
Yeah,
sorry.
any other scalar would
Yeah.
work, not just this one. Any other scalar would work. You can ignore all of this, even though this is there in your code. You can do the timing part. I think the timing does make slight difference in fitting the model for this small data, just like few seconds. This is where we are fitting where we are importing the instance of the PCA, and then we are fitting on our scale data, right? So this line is clear. And when we do the explained variance ratio, you will see that there are how many components? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the number of components will be exactly equal to the number of features by default. But then point is where exactly the dimension reduction is happening, right? So that's where this is actually coming in. What it means is from your overall data's explaining power, 36% of that explaining power is captured by the first component. 19% is captured by the second component. 11% is captured by the third component, and so on and so forth. So if I do a summation of this, you will see 1. So all these components together explain 100% of your data's explaining power, right? But I don't need all the components. I need 80% explaining power. So what I'm going to do is...
Sir, one question there. When we did the linear regression or logistic regression, we also got this similar numbers, which said, okay, this one is contributing so much to your output computation, something like that.
Yeah.
So how is that and this are different?
This is like the eigenvalues actually, and I'll show you the eigenvalues as well. So it's basically when it does the linear combination of the variables, it is combining in a way that the first component captures the most variance in the data. So, I mean, if you're looking at the x1 to x2, it's not necessarily looking at anything, but it's looking at the range of the x1, range of the x2, range of the x3. And it's saying like, let me capture the maximum of that, right? So what it basically means is it's not explaining a dependent variable. It is saying only from the independent variable, I can capture 36% value of your independent variables. Whatever information your independent variables are capturing, 36% of that I have. Principal component 1 says, right? Principal component 2 says I have 19%. So no correlation to dependent variable at all. The one that you're looking at earlier is about the dependent variable. Remember, we're just looking at the X. There is no Y over here, right? So it's all the like variation. Explaining power is variation. Like your original data's variation, how much of that is being captured in first component, second component. And you'll see they will come down. First component will have the most, second will have the second, third, and so on and so forth. So it will continue to trend down, right? And this is our assumption. So if you add up like 1, 2, 3, 4, 5, you'll see it comes to around 80%. But I'm just doing it so that you can be rest assured. So I am saying now fit a principal component with only 5 components. So instead of doing the earlier where I left it alone, I'm saying now fit a PCA with 5 components only. And I'm fitting in this data. And then if I do the explained variance ratio, you can see it's 80%. So what it means is instead of taking my 13 original features, if I take 5 components, and if I do a PCA with those 5 components, they give me 80% of the data's explaining power. And this is a good rule of thumb. So in case if you have to decide what is the right number of component, you can say 80% is good enough. If I can capture 80% of my data's explaining power, I'm more than happy with that, right? So that's what it is telling you, that you should have 5 components. You can say, okay, what if I do 6 components? You can try to change that. I don't know whether I've run the code or not because it's a random for us also, but you'll see this number jump up to, if you add up these, that's 6 or 5. That's right. So you will have like 85% with the 6 components. Then you will have 88% with the 7 components and things like that, right?
Yeah, one question. I think I got confused these numbers with X1 features explainability. I think this is P1, P2, P3, and like 13 equal to the number of features that is there
Originally
by
it is equal
default.
to number of features, right?
So this actually principal component part, not actually the explainability of X1, the first feature on the Y.
No, there is no Y here. Only X. Only X.
Got it.
So it is saying that if you take away all my X's and if you just have one component, that original X's variation, 36% of that will be captured by first component.
Yes, got it.
19% will be captured by second component. So I'm saying, okay, I just need to capture my 80% explanation of the original data. That's why I actually went with the 5 components. Right. So if you do 6, then you'll get 85. If you do 7, then you'll get 89 and so on and so forth. And this is what I am talking about, the eigenvalues, right? So if I went with the 5 components, then I'm going, remember those are 2 different things. Those are explained variance ratio, and this is explained variance. This is eigenvalue. And a simple interpretation of eigen or eigenvalue is, it is saying that the first principal component is as good as 4.7 variables. Right? So the first principal component is as good as 4.7 variables. The second principal component is as good as 2.5 variables. The third one is 1.45 variables, right? The fourth one is 0.92 and 0.85. That's what basically it means, right? And again, they will go in the diminishing order, that the first component will be the most useful, the second component will be the second most useful, and so on and so forth. Right? You can execute later on. Just understand what we're doing. Yeah.
2.7 times.
So like, 4.7 variables worth of explaining power is being captured by this component. Like, I mean, you have x1, x2, x3, x1, x2, x3, all these 13 variables, right? So you have these, right? So it doesn't tell you which variables, that I'll come to later on, but it says, if you have alcohol, malic acid, ash, and magnesium and total phenols removed, just one of this component explains all of them. That's what basically it captures, right? So it says you don't need to have alcohol, malic acid, ash, magnesium, total phenols. You just have me, and I'll explain everything that they were explaining. That's what the 4.7 really means. That one component is as good as 4.7 variables. Second component is that I will come to. That I'll come to. That you'll be understanding from the loadings. That's how it is designed. So when you are doing the
does it mean that alcohol here?
No, it won't mean that alcohol is going to be the highest one. It could be any other variable. When
It is like out of 30 features, it has just arranges the order,
Yes.
but it can be anything.
It can be anything, not the alcohol. So it doesn't mean that component 1 is talking about alcohol, component 2 is talking about this. It doesn't mean that. It can be any random linear combination that we're looking at, and I'll show you what that linear combination is. But this is the most important component, second most important component, third most important component, like that.
Sir, in other words,
So,
instead of having 13 features, if I just have one PCA, that is a P1, it will take care of roughly five
Correct. Yes,
variables.
that's
Okay.
correct. That's correct. So if you remove everything, just build a PCA with one component, you will still account for 4.7 variables
Variables.
worth of information. Similarly, if you just have two components, you will still explain 6
6 variable.
point, or I mean 7.2 variables worth of explaining power of the variables, right? That's the eigenvalues. The earlier one is the ratio, which is what percent of my data is explained by these components. Slightly different concept. Okay, this is where we are talking about the loading. So PCA components, and then we're gonna have the X dot columns, right? So we are creating a data frame. Remember now I have only 5 components because we have decided 5 components is the right one. So I'm describing the components and putting the value, right? So how would I know what is component 1 or the component 0 index? That is 0.44 times alcohol, 0.24 times malic acid, 0.002 times ash, 0.23 times alkalinity of the ash. Remember the alpha 1, x1, alpha 2, x2 I was explaining earlier? These are the alpha 1, alpha 2s, alpha 3s, alpha 4s, alpha 5s that it is coming out with. And if I do a plot of that, which is right over here, now you can see, if I look at the principal component 1, you have to go with the top 2 or 3. Where is the value the highest? So what do you think is the highest value, either positive or negative? So I see 0.42. What else is there? 0.39 and 0.38. So 0.42 is flavonoids. So you can see principal component 1 has nothing to do with the alcohol actually. In fact, it's driven by flavonoids. So it is a proxy for flavonoids as the highest contribution. Second highest contribution comes in from total phenols in P1, right? And the third highest contribution comes in from the whatever that variable is. It's a long one, right? So that is the loading of this component. Similarly, the loading of this component, second component is 0.48 the highest, and sorry, 0.53 is the highest. So you can see color intensity. And more often than not, you will see that the same variable will not be heavily loaded in all the components. So one component will have heavy loading of one variable, the other component will have the heavy loading of the other variable. So when you say P1, somebody may ask you, what do you mean by P1? What does it really mean? So you can say basically it's a weighted average of all the other variables, but over-indexed on flavonoids, over-indexed on these. So generally there is a good practice, like you state top two or three loadings of that component, and that is what we are actually capturing there, right? Similarly, the third component, let's see which variable it picks up. Where is it? 0.66, sorry, no, 0.06, that is. 0.54 is the highest I see, 0.54, right? 0.54 is the highest. 0.54 is malic acid, right? And so on and so forth. So that's what the loading really means for the components. So again, I will explain you. It says you don't need to do that. I mean, your algorithm does not require that, but just for your understanding, what I'm looking at, right? So your P1 is nothing but 0.44 times alcohol, 0.24 times malic acid, 0.00 times ash, and so on and so forth, right? It doesn't matter. Minus, plus, it just basically means which direction. It's a vector. Vector has a magnitude, vector has a direction. So it's low on color, low, high on this, like that. So vector has a magnitude, vector has a direction, right? So that's what we are looking at. And it just helps you sort of like, visualize what we are looking at, right? Now, this is slightly tricky to understand. A lot of people don't get this concept. Why suddenly my 13 became 5 and how did we come out with the 5, right? So I'm just going to explain you that math very quickly over here without straining too much. I know it's the end of the day for you. So let's say x1, x2 till x13 were there, right? They have been shrunk down to P1, P2, P3, P4, and P5 for the same observation. I'm just making up certain value, like I mean 0.2, 0.3, blah, 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 0.9 value was there, right? And this is row number 23. So row number 23, when we have converted the PCA, will look like this. There is no X1, X2, X3 anymore. They will be P1, P2, P3, P4, P5, right? And P1 will be nothing but your alpha 1, X1, alpha 2, X2, and so on and so forth. And that will be basically one value which is thrown there. Similarly, P2 will be beta 2, X1, beta 3, beta 2, X2, beta 3, beta 3, X3, and so on and so forth. One value will be replaced over here. And then this value, this value, this value, right? So that's why nothing happens in the row. The only thing which happens is instead of X1, X2, X3, X4, I am having a linear combination of them to replace them in the P1, replace them in the P2, and so on and so forth. So that's why this column gets shrunk, nothing happens in the row. Row remains what it is, right? Because I need to have the row to capture that value. So that's what happens over here. Oops. Okay, next time I have to fix it. I don't know what. All right. Otherwise, I will get lost. I mean, what changed over here? Very small table actually for working. This laptop, and I have to fit so many different things, right? So I just need to have bigger space actually. So we should continue. And then this is the loading part that I was explaining you earlier. And then once you're happy, this is where we are doing the fit transform. Remember, till now we've just created the instance. We've done the descriptive of that instance. This is where we are doing the fit transform on the scale data. Now, after you do this, your 13 columns get shrunk to 5 columns. You can see the difference coming in over here. Rows remain the same, 178. Rows remain the same, 178. Your 13 columns have been shrunk down to 5. Why 5? Because I chose to have 5. Why I chose to have 5? Because they explain 80% of my data. Why I need to explain 80%? Because that's a good rule of thumb that I should follow, right? Now, this is what is going to happen after I do the shrinking of that using this. I have to name them because it doesn't know what exactly I'm looking at. So I have to name them that I'm no longer the X1, X2, all of that. So I'm P1, P2, P3, P4, right? And that's how you see that these 13 columns that you had originally have now been replaced by your P1 to P5 and 178 rows continue as it is. I hope this concept is clear. Yeah, definitely. You can ask me. I mean, we still have time. But that's what it does basically. That's what the PCA is. Now, if you go and do a correlation again on the PCA, X scale transform, you see 0, 0, 0, 0, 0. Absolutely no correlation among all the PCAs, right? And that's the beautiful thing. So any algorithms which are super sensitive to the multicollinearity, X1s being independent, and all of those assumptions making, you can say, fine, I'm just going to give the principal components, be quiet, and the model will happily run with that, right? So because there's no correlation at all. This is the most perfect approach of fixing the multicollinearity. Other things you can drop one variable, drop that variable, all of that. I mean, you can still never fix it completely, but this is the rock solid way of fixing the multicollinearity, as well as reducing the dimension, as well as getting more signal, making your algorithms run faster. Sometimes your algorithms being more accurate also because of the PCA. Right? Okay, I'll take a pause and open up for any Q&A on this.
Okay, so to run further analysis on this, let it be a classification or regression algorithm. So this is the start point.
Yes.
The end of this is the start point for those
Yes.
next analysis.
And the code I've shared with you, you can follow along with this. So now instead of putting the X scaled my original data, I'm putting X scaled transform.
Okay.
So it will no longer use the original X, it will use the components only. So this is going to be, you know, your, you can see from over here, right? So instead of the 13,
yeah,
it is 5, 5, right? So these are the number of rows that we're looking at, number of columns that we're looking at.
Okay. Now, if we use this, the transformed data, how are we going to eventually interpret the results in terms of the original variables?
Yeah, that's a great question. And we lose the interpretation part a little bit when you do the PCAs, because your PCAs may give you directional loading of that, but they will never tell you exactly what that component was, right? So they're not very interpretable. So when you don't really care about the final interpretation in terms of the component, but you care about the recall, precision, models performance,